from hydrostatic, and you need both. Both this and the Ampere's law. I mean, the way we do things is slightly different, so it looks like we emphasize more on this part. Oh, wait, this brings up J, and then the divergence of P is equal to 0. Right? But these two are equivalent. So you have to be able to do both. And in fact, most examples, you have to combine both to be able to actually solve it. Right? For example, I don't know if there is one in your homework, but let's get to that later. There are two problems that are difficult, it seems. At least the one that I already assigned, but my thinking right now is not to assign anymore. Okay, let's start with the last one. The second to last is actually mostly qualitative, but if you know how to solve that, it's just some wisdom in understanding of quantism perhaps. One by Starbuck law and Ampere's law. Any question? If not, I'm going to look at problem 670. 670, a two-dimensional plane. Of course, things are in 3D, right? So there is a B field out of the board everywhere. I think it's out of the board, not in the board. Yes, in the C direction. Whatever, either in the board, out of the board, doesn't matter. As long as you define it, right? And then this is the trajectory of the particle that we see. It's a spiraling motion and it's drifting in the y direction. Right? And the question is, what's happening here? And is there an electric field? And if there is, something to give you all the numbers. So how strong, in what direction? So let's see. If all we have is a magnetic field, right, and that this is like 4, right? If I have a magnetic field out of the core, right, and if I have a particle, a charged particle E, positive E, right, E is always positive, and when it will perform, it will execute a circular motion, right? And you did this as a homework last week. What's the radius of curvature? Okay. It's P over P is the momentum, and the momentum is, so you give it an initial velocity, right? The momentum is gamma and V. Remember, momentum is always gamma and V if things are relativistic, right? Of course, if things are moving slowly, then gamma can be slowly down, right? So P over, is it NV, something like that, right? So it's, no, it's not N, it's E. Gamma N V over E. Something like that, but it's a circular motion. Maybe I'm wrong. Am I missing something?
It was QB.
Oh, yeah, Q and E is the same thing. Yeah. I guess I should use Q in this case because, I don't specify whether there's a photon or whatever. Okay? So how about here? Where is the direction of the electric field? Any guesses?
Wait, what's moving? So is this an electron moving?
It's a whatever, charged particle plus Q in. And it's executing motion like that. And it's drifting with some drift velocity of V in that direction.
Because if it didn't have any
so would it
electric
be in
field.
that direction?
Yeah.
Or if it's QE and if it's drifting in the y direction, then that means there's a force on it.
Right.
Or
So
pushing in the y direction.
so it's drifting in that way and it's going around, sort of, right? It's a circular motion, but it's drifting basically, right? Something is pushing it sideways, right? If there is no electric field, then it's going to go around, right? Just round and around, and it's going nowhere, right? So how many of you think that the electric field is in this direction? There's an electric field in that direction.
Like,
Just for fun.
was it a perpendicular thing? Or F equals QE is in the same direction, right?
Yeah.
Wait, what is E from?
No, the question asks for, well, you give it that there is this motion. and you deduce if there's an electric field. Because if there's only magnetic field, it will just execute a circular motion.
But it's not doing
Right?
Yeah.
But it's not doing it, it's not a circular motion, so there must be electric field somewhere. The magnetic field only gives you circular motion. Right? And this motion is confined to 2D.
Yeah.
And it's not an ideal exercise or pedagogical exercise, say in the case of a Hall effect, or quantum Hall effect, fractional quantum Hall effect. Things, electrons sometimes move into dimensional space. Right? Or in the inversion layer, the semiconductor that we talk about, the H7B. Right? So this thing is moving in 2D, moving in the y direction. Let's go fast. How many things electric field is in the y? How many things is in the x?
In the Y.
I think it's in the Y direction.
Y. Okay, how
Yeah.
many things is y? How many things is x?
Are we all wrong?
Who wants to be a contrarian here? The answer is x.
Why is it in the X direction?
Yeah, well,
Okay, let's do it.
There's some cross products.
But there's something I'm missing in this article.
You might always have good insight there. Yes, because of cross product. So remember, things are always simple when it's not moving, right? And in this case, it's not possible, but the closest thing is it's a circular motion. Right? So if I go to a frame, if I jump in this frame, right? So this is Charlie's, right, in O prime, right? Where I'm actually following the drift, right? Then it will be a circular motion, right? Okay. So in that frame, well, that's O frame, right? This is the frame of Iman, right? It is O, you have frame, and this is Charlie's frame, moving.
We totally switched to Charlie.
That Charlie was
Well, the thing is that, you always have to switch back and forth, right? So, unfortunately, because of, I don't know what happened, suddenly Charlie is the one who's moving and not this is, right? But the problem is we have to switch back and forth twice, just like in chapter 5. So in O prime frame, it's a circular motion, right? And there is no electric field, right?
Right.
Yes,
Is it starts going like in a spiral like this, or is it?
It's in a spiral like that, right?
So it's actually that's the. That's
Well, it's
actually
actually given, the problem also gives you that it's sort of like a circular motion or a cycloidal motion.
It's not like helical.
Yeah, is
No,
it helical?
No, it's not, it's in the XY direction.
Okay.
It's more like a, so it's confined in 2D, it's a 2D problem.
Oh.
Right, 2D problem with a piercing of magnetic field in there.
It wouldn't make sense to do it the other way because B is pointing out of the board.
P is out of
Yeah, they
field.
wouldn't
It would do motion this way.
Think of this as a 2D problem with a P field out of the board, right? So in this frame, remember the transformation, right? E prime is equal to gamma E plus, remember this is plus. Also remember in this case here, right, the sign matters a lot, especially in the midterm, and then in the exam you get confused, right? It's time pressure, sign matter, you make a mistake. This is the problem with the midterm. If you make a mistake on part A, the mistake propagate, right? And how do I actually grade it properly so that I don't like penalize you too much, right? Because if I just, well, this is a mistake from part A, part B is a mistake too, part C is a mistake, then what do? I guess just
They
go
don't do
zero.
that in Jeopardy.
That's hard, right? And then I'm like, well, so
Assuming that you got
somehow
fine.
having a lot of difficulty.
Yeah,
with
you
exam
correctly
this
part
time.
B, then.
Maybe I just don't know how to grade. Next term, I'm going to get a GSI for sure. This is just impossible for me. Sorry?
That is good GSI.
Well,
Get a GSI that doesn't grade the midterms the way your GSI
well,
grades.
you know, maybe
them.
one can become
That's
over.
what she said.
So it's E cross B, and this B is the velocity of O prime. So it's the velocity of O prime with respect to O. Okay, this is velocity of O prime with respect to O. Okay? So this velocity relates the Lorentz transformation between O and O prime. Okay? So So in this frame, in Charlie's frame, this is 0, right? That's why it's a circular motion, right? Therefore, gamma, well, what does gamma matter? E plus B cross B is 0. So in the image frame, E is equal to minus. I guess I pretty much solved the problem, except I have to put in other numbers. Somehow the problem asks for numbers.
Ew.
So it's actually that way. It's completely different.
How does that work though? Because like if you look at like in the last frame, the particle, because the magnetic field's pointing out of
Yes.
the door, then it's gonna if there were no electric
With
field, it would
respect to-
execute like a
Right,
circle,
yes.
right? But since it's moving in in a y direction,
Okay.
then there has to be a force pushing out in the y direction.
Very good
But if
question.
the electric field's going in the x direction, then it would produce a force going that way.
Right.
Not so fast like a spiral, but like what does it keep
Yes.
going up?
Yes. No, it's a good thing to pursue, right? I mean, maybe we don't believe in all this black magic, right? We believe in Newton's law, right?
Where was there an, it was because if you take V and cross B, you get X, right? That's
Yeah,
how you
so, maybe I should elaborate this a little bit, right? So V is in this direction, right? There's V cross B,
Okay, and then
right? And there's an E field in that direction, or in this direction, I don't know, minus X or plus X.
Right.
Right, you have to do the right sign, right? You don't have to be careful in front of the board, but you have to be careful in the exam. But no, good point though. That if you can, so let's do this in briefly, right? Just to give you motivation. Like do it in the completely in image frame, in the O frame. Right? Forget about O time frame. So there is a say there's an electric field in the X direction. And then there's a B field in the C direction. Then solve for the Newton's law. X double dot then is equal to Q dx, right? Okay. But you must also, if you have a component of I guess plus or minus, I don't remember. Right? It's always y dot times dy times v naught, right? Because this is the cross of velocity in the y direction, right? With respect to v, will give you an acceleration in the x. I just don't remember the sign. I'm just motivating you. I'm not solving this, right? So you're gonna get a couple of differential equations, right? So m y double dot, right? Everybody knows double dot is differentiation with respect to time, right? Becomes here is q times 0, right? There is no electric field, there is no electric force in the y direction, right? Plus or minus, I don't remember, or I didn't bother to look, x dot times v naught. Right? So this is the coupled differential equation that you have to solve. Right? When you solve it, you get a spiral case like that moving in the y direction. In fact, somehow I remember, this is the home, this is one of the homework problems in physics 110. Solving, this is a couple of differential equation. When you solve for it, you'll get x. X is going to be some x naught.
Oh, you get the full motion, including the.
Plus p, right? And then y is going to be y naught plus v, the drift velocity times time, something like that. You will get something like this. And this depends on the initial condition. V naught y. Sorry?
Are both of those x dots next to the top one y?
Top one is Y.
Top one is right there. Right. So y crosses, velocity in the y crosses p, gives you a force in the x direction with a minus sign. Right? And then force, velocity in the x crosses p, gives you an acceleration or a force in the minus y direction. Right? You solve for this equation, you get that motion. Forget relativity.
Shouldn't the y variable also have like a sinusoidal term when you solve for it?
It's got
Because it's also.
yes, there is, you're correct. There is a drift term and there is also a cosine term. Yeah, yes, correct. Yes, sorry for that. I forgot. Right. So there's a drift term and a cosine term.
Doesn't that mean you have to know which direction the field is already going down?
Right. So well, you solve for it one way and well, you can put no, it doesn't matter. I suppose you start with the y, right? Then this thing will be different. And then you know the motion is going to like go in that direction. Right. In this case, the field is in the x direction. You get something like this. Okay. So that's number 17. So this is a bit counterintuitive, right? As from the pole, right? But hopefully now I convince you. At least relativistically I convince you, but maybe not from the differential equation. It's not that obvious, that solution is there, right? But from relativistically, it's very clear. Right? The field has to be in the x direction.
If you had the magnetic field in this case pointing in the y direction, then if you also have the electric field pointing in the y direction, could you get similar motion?
If I have a B field in the y, yes,
and then you also have the E field in the y direction, would that be the same thing?
Yeah, except that this thing will. The electron is confined in 2D plane. Right? But in that case, then you have a spiraling like that going like that. Right?
Yeah.
It's a helix. It's a
Is
complete.
that what this is?
No.
Oh.
This is completely 2D.
Oh.
The electron move in, sorry, the electron completely move in this, the electron is never leave the black hole.
Oh, okay.
Right? The electron is always on the black hole.
Okay.
Is that clear?
No, you already said that.
Yeah, you said.
Yes.
Is it really going to be circling around though once you release it, like a charge in a constant B field?
Yeah, if there's any finite kinetic energy, right, you can launch it with any velocity. It always, if there's any B field, it will always execute a certain motion.
No, I mean like, will it spiral towards into itself at all, or will it just stay in a circle?
That it would actually stay in the circle. What do you mean?
No, like, would it stay in a circle like this, or would it spiral inwards?
Oh no, it would. Well, if you consider radiation, then it will eventually lose its energy, right? But if there is no radiation, it will go like that. This equation, by the way, is one that made Berkeley famous, right? I mean, well, I don't know what really made Berkeley famous, but the cyclotron, right? I like to think that maybe it's Oppenheimer that makes Berkeley famous, not really Lawrence. But I don't know, but Lawrence is everywhere, right? But Lawrence is the first one who had the cyclotron, and this is what he found relativistically. He was not doing it non-relativistically, because you try to accelerate this particle to really high velocity, right? And he found that this and then the period. The period is I don't know. The period is independent of B. So you can always, this whole thing will be periodic. So you can always accelerate the particle a little, asynchronously. Right? Because he has this two plate, right? In a P field, and every time a particle, this is a parallel capacitor, right? So every time a charged particle flies through this parallel plate, it gets accelerated a little bit, right? So you go on like that until you hit a target. Right, at very high velocity. And I think the thing that made him happy was when he was actually realizing that the period is independent of the momentum, or the half period is independent of the momentum. It turns out he wasn't the only one. Leo Szilard also actually patented the idea earlier, except that he wasn't that good at executing it. So he only had the fact that he doesn't have the device. Anyway, that was a bit of a historical story. But yeah, that's the reason that we have a blossom in physics department in Berkeley in the 40s, 50s. And the next one is actually interesting. It's a solenoid and superposition. Have anybody seen this before? Again, I don't have much time, and looks like I'm always veering away from Balsada law. Maybe because I don't like to read the codes. So, go through well, let's see, I don't want to repeat the problem, it's a long problem. But the idea is to find out the character of if I have a finite solenoid. There's a current here, and the PQ is going up. There's a winding number n, the number of windings per unit length, and the PQ is, people remember this from Ampere's law, what's the PQ here equal to? Yeah. Not. Okay, in the C direction. First question. The first question is, in a finite length solenoid, find that the magnitude, so if this is called P2, and somewhere deep in here is P1, show that the P field at P2 is half the P2 at P1. In fact, it's actually greater than half. How do we do that?
Wait, P1 and P2 are arbitrary points?
Well, P1 is at the edge of the solenoid. So the solenoid has an edge, right? We're talking about not an infinitely solid, it's semi-infinite.
It's infinite going down.
Infinite in that direction. Right? It has an end. Find the P field here. Right? So how do we do this? So you just have to you have to muscle all your understanding of Balsada law and Ampere's law, right, into just not really quantitative but mathematical analysis of the situation. And then we use this because this is irrelevant for now. So what do you do? Principle of superposition, right? By Balsada law, you know that the P field here at the center is pointing like that. Right? This is the P2. Right? And if I have a solenoid like this, infinite in that direction, with the same sense of winding, right? So that the P field is going that way, right? Always the right hand rule. Then this is P2, but the field goes that way, right? Okay. So if I put two of them together, with the same winding, it shows the same winding. Because if this is winding like this, if you flip it, no, you put one on top of the other, so you don't flip. So basically you slide this whole thing, you put the other end on top of it, right? So it gives you the same winding. That, so this is BP2, here's also BP2, right? And they touch back to gut. So then the field here, right, is it. So this is around here and P1 is around here, right? In that case then P2 and P1 are kind of the same thing, right? By symmetry, right? So then 2 dP2 is about equal to dP1. Right, so dP2 is about half of the dP at dP1. Okay.
Where did the greater than or equal to come from?
Yes. Right, that's nice. Right.
Wait, where did?
So right now it's an equality, right? Right now it's equal. Right. Everybody understand why this is the case?
No, why were P1 and P2 the same?
Because if this is semi-infinite, P1 is over here, right? So it's infinite in that direction.
No.
And it's infinite in that direction. Right? So at that point, there is translational symmetry, right? Point at P2 and point at P1 is the same point. It's the same, has the same symmetry, translationally invariant, right? From P2, everything is infinite in both directions. From the point of view of P1, everything is infinite in both directions. Right? But the field at P2, I'm just but joining these two solenoids, right? And one of them has a field going outward. The other one has a field going inward, because this is the other end of the solenoid. Right? I travel to infinity, to the other side of the other solenoid, and find that the field goes like that, right? So that's the case, right? But in actuality, well, the problem asks for more, actually. I don't mind if you stop over here, just like that, because it has no bearing on the rest of the problem. But since the problem asks for it, but suppose this is not completely infinite, suppose this is kind of finite, right? It ends somewhere. Right? Then this also ends somewhere. Right? Then you see the field at P2, right? Whatever twice in P2, right, is larger than P1. Okay, so P2 is larger, somewhat larger. I guess it becomes equal if this thing goes to infinity, right? But it's larger or equal in half if it's finite.
Is that just implying that near the edges it would weaken?
Yes, we can. Yeah. By itself, I know that you guys are very busy, but there's only finite amount of time, but you should do some exercise of Bayes-Savart law. In fact, the book has we actually goes to the Bayes-Savart law for solenoid as a function of where you are along the axis of the solenoid. You should go through that derivation at least once, and then you'll see that actually the field. If this is if it's a finite solenoid, the field is the strongest in the middle, but it's always, at least along the axis, it's always like that. But it's the strongest in the middle, right? And it's only half of it here. Right? So it has to be somewhere in between.
Is the B field constant within the solenoid? If it's infinite?
Yes, constant.
So it doesn't matter.
But if it's finite, then if it's finite like this, then yeah, it's constant over here. Then start to deviate.
Okay.
And that's the purpose of the problem. Right? This is why we have to solve this problem here, right? Because that's what part B, C, and D walk you through that. Right? So let's see. B, right? The B you're supposed to show. But which one can I use? I can use that one. You're supposed to show that if I have an semi-infinite solenoid like this, right? As you said, there's field lines, right? And the field lines will start to deviate from vertical, but show that just right here or at the edge, the field goes like that. It's not like this, it's not like that, it's actually straight out, horizontal. You start to ask, what's the point? Do you have to do this? You can use Bayes-Savart law if you want. But Cranton was in the audience yesterday at the talk on electron-electric dipole moment. From the top, that's a pretty impressive experimental setup, right? Stray, you have to worry about all the stray field, right? So, so you have to know your fields. Right? Not only you have to know your field in here, which is easy, you can just use physics at H7B, but when you're doing a real experiment, if you're looking for some really minute effect, right, then you have to know what's stray. And that's the purpose of this program. do we do this? This is also an exercise in principles of organization. How do we do that? Proof by contradiction. Suppose the field here, suppose the field here actually has to be more realistic as it was. Well, it doesn't matter because the answer is 3. Suppose the field here has a component like that. Right? So it not only has an actual component, but it has a radial component. Right? We know it has a radial component, right? Because we know in the middle here things are straight and it starts to veer out, right? But just right at the edge, it goes straight. That's the claim. Right? So, make sure the winding is correct. So the winding is right-hand rule, right? So if this is true, then suppose I flip this whole solenoids to the other side. Right? So in this case, let's make sure the winding is correct. The winding is like that, right? If I flip it, right, physically flipping the whole thing, right? So the winding becomes like this, it becomes like that, right? So it actually goes that. Right? And then there's a B field in this direction, right? Okay? Therefore, if I look at this point will be, this point will be, how are you going to write this in your homework? I don't know how you're going to do that, but you can always discuss in words. So over here, then if I flip this, then there's a field going like that. Right?
Wouldn't it be down?
Yeah. So what do you do here? Take it like this.
Down into
like
down into the left.
Yeah, so it's down into the right, right? Like that, right?
Yeah.
This right? If I take this thing here, and turn it 90 degrees, it will look like this, right? Okay? Okay, but you know where I'm going, right? I'm trying to couple these two things, right?
Mm-hmm.
But I can't because the sense of the magnetic field is wrong, right? This has a winding that looks like that, right? This has a winding that looks like this, the opposite sense, right? So you need to flip the current, right? So if you flip the current, and you try it again, flip the current so that it actually goes like this, right? Then at that point over here, the same point, right? Let's call this point not P3 or something, right? And at this point, just from Savart law or Ampere's law, right? Flip the current, flip everything else, right?
Wait, so you just reverse the current?
Yeah, then you reverse the current so ideally I want to couple this on top of that, right? Okay. So I have to reverse the current, right? I reverse the current, then if this B goes like that, then this goes like that, right? From Savart law, you change all the current, flip all the current, all the B field flip, all the B field flip, right? So now I can just couple this and that, right? So you see, if I, of course, I have to rotate this, this thing is cylindrically symmetric, right? Right. So it's over here, and it goes like that, right? Okay. So I now couple this on top of the here, right? Okay. Then I have an infinite solenoid, right? But there is a B field like this, so the resultant B field is like that. Right? So we know for a solenoid, the B field is 0 outside. Right? So that cannot be true. Whatever our original assumption is, right? Over here, you cannot be cannot have an axial component. Cannot have axial component. Because it leads to a contradiction. The B field has to be in that direction, has to be along, has to be straight by the continuity of the flux line. It has to be in that direction.
Wait, for the last step,
Mm-hmm.
you superpose the two B fields,
Yes.
so you get a B resultant that's vertical,
that, yes.
and that one is illegal, you can't
That's
have
illegal because in a solenoid,
that. Yeah,
the B field outside of the solenoid is zero.
but we've already established that there is a B outside the field solenoid,
No,
going
only,
that way.
only,
Only
yes,
axial?
yes, semi-infinite.
Right.
At the back end of the solenoid, there's a B field, right? So you in an infinite solenoid, the
Right.
B field is confined, completely confined to the flux tube. There is nothing outside.
Right.
So I used that to prove that with the contradiction that there is no, there cannot be any.
Oh, because you constructed an infinite one.
Yes, I
And
constructed
the
an
field
infinite
outside.
one, right?
Gotcha.
That shows that there is B field solvent, right? Therefore, if there is a B field, then it has to be radially upward. Otherwise, you just like it.
What about if the solenoid is not semi-infinite but just finite?
Even if this is somehow it's finite, then
Then outside the B field isn't necessarily zero.
it's then it's you have residual effect, right? Because but if this is long, if I look at point very close to this to this end,
Yeah.
right? Then as far as this around this point is concerned, this is infinite,
Okay.
right?
So for finite solenoid, very close to the outside.
There might be a small residual of an order, 1/p squared or something, right? You might have an actual component, but that's merging, that's completely making this whole emerging because there's a long discussion here that rely on the fact that this is infinite. I don't want to pursue that subject because it will confuse. This is already confusing. But yeah, if this is semi-infinite, then this is exact, right? The B field has to be straight. Right? People understand that proof?
But why is it that the infinite case has to do with the non-infinite, semi-infinite?
Oh no! We want to look at the problem. The problem actually asks for. We want to gain understanding, as I was telling earlier, that that straight fields are important, right? I want to understand if this is a solenoid. I want to know how the field looks like at the end. We know deep inside the B field is mu naught and I.
Yeah.
Right? And now we know that here is half of mu naught and I. Right? But how about here? How about here? How about here? Right? And now from part B, now we know that it has to be like that. Right? So we know this. We know half of mu naught and I at this point, we do, and we know this is straight. Right? We don't know the magnitude. Right? I mean, at the end of the day, you can always put this in a computer and simulate it, right? I don't know, console or whatever. It's very simple. In fact, you probably can do it on Mathematica by H7B law, right? But this gives an understanding of H7B law and Ampere's law and the divergence of B field equal to 0. So that you can
And it has
have
an
an
axial
sense.
component,
Yes, it cannot. At the end, it has to be radial. It cannot be axial, like that proof. Because
it
if
can be zero on the outside, but isn't that still a B field?
only if I plug couple two semi-infinite
Oh.
solenoid. Like if I plug couple two semi-infinite solenoid, then the B field outside is zero. Otherwise, it's not zero. Right? And we just show it just by thinking and by arguing, right? Not even doing any math, right? That it has to be radial. Right? This argument, by the way, doesn't work inside. Inside here, there is a radial component. As you see, there is a radial component, right? But there's also an axial component. Right? You can do this proof of back contradiction, right? This rely on the fact, when you do the proof by contradiction, rely on the fact that at the end of the day, the field outside is zero. But the field inside is not zero. So symmetry is broken there, right? So in that sense, this argument failed inside, and inside there is an axial component of the P field. Is this clear? Is this confusing? I hope it's not really confusing. I want to stop with that, just this 5 problem, because we all difficult. Any more thoughts?
I just want to triple check.
Yes,
So
yes.
with the solenoid,
Uh-huh.
if you're going straight out from outside of it, say it's going this way.
Yes,
You're going out this way.
Uh-huh.
Outside of it, field 0.
This is, if I have a solenoid.
Yeah.
Okay. Zero. Yes.
All right, so
Zero everywhere.
So-
This goes to infinity. Zero.
okay. And if it's not going to infinity and you just cut it top to
So
bottom,
cut the, say if I cut here, let's make it easy, let's cut the top half, right?
okay.
Yes,
So then going up out of it,
Yes.
you're going to have the field spread out and
It's still like this.
diffuse to where eventually it's going to just reach flat and very small.
Yeah, oh yeah. It will diminish in magnitude as it goes out.
All right.
Remember the B field line? Oops. The B field lines always, it's form a loop, right? Everything is loopy, but not static, right? The B field loops, the current loops. You cannot have any source in static. Everything is loopy. The current always loop. The B field always loop. It's,
If the solenoid was not infinite at all,
Uh-huh.
finite,
Uh-huh.
then does that loop around that way?
Yeah, that if this is somehow kind of finite, right? Then this is no longer true. This actually, you can acquire axial component, right?
Wait,
But-
what?
If somehow this is short and stubby, right? Then it's different in character a little bit. You acquire residual axial component.
So then you have magnetic field outside the solenoid, then, right?
Yes. No. Here also you always have magnetic field outside the solenoid. If this is cut in half, you have that. Right? And in fact, it's start to, as you will show in CMD, it will start to leak.
Oh.
It will start to leak.
If it's not
Semi-infinite. If it's semi-infinite. If it's semi-infinite, right? This is infinite. You will show. I mean, that's I have like 2 more minutes of CMD. You will show that this thing has to leak out through the side, through the wall of the solenoid.
But if it's a perfect infinite solenoid, then you just have it inside.
Sorry?
But if it's a perfect
Solenoid.
that's infinite length.
Yeah,
you
if
only have
a
it-
perfect solenoid, then if it's a perfect solenoid, it's always zero outside. Right? If this goes to infinity, then it's zero everywhere else. Yeah, it's zero.
If it were a finite solenoid, the center on the outside would be the magnetic field would be zero,
Center on the outside.
So
This is
it's
what?
along the axis.
because they come together.
No? If this is cut like that, then this goes like this.
So, but in the middle of the solenoid, not the center, sorry, but
Along the axis.
Center of the
The solenoid on the axis.
no, outside the solenoid, but in the center,
Yeah.
middle, yeah,
It's non-zero. It looks kind of like a dipole.
but at the surface, at the core.
At the coil. Not quite sure. I don't
Because
think
one
so. I think
one
it's
part
wrong.
points out, one part points in.
Well, yeah, actually that center like that Salvador it's zero. Right, but slightly out, immediately you get leakage. Okay. Right. The thing about magnetic field is it always forms a flux tube. right? And you'll see more and more of this when you study statistical physics, superconductivity, and all that. Magnetic field always form a flux tube. It never have an origin, always loop around. Right? And in the study of magnetostatic, current also always loop around. And then you can't do all those that magnetic. So with that in mind, but you have to show, it turns out you have to show, and you can show this also by similar method like this. Maybe we can talk about it tomorrow, right? This is probably the most difficult problem, at least conceptually. That here, everywhere along this point, okay, this is semi-infinite, everywhere the B field in the axial direction at P, and P can be anywhere along here, okay? It's always half of mu naught and I. So it's always half mu naught and I. Okay? The axial component. It has a radial component, but I don't care about the radial component for part C, I think. And then you show that the flux, this is the flux through the top, then it's just is half of P naught times the area, right? And here, but the flux through here in the middle, the flux here is P naught and P naught times area, right? Area is the area of the solenoid. And P naught is mu naught and so the flux in the middle is twice the flux at the top. So if I want to trace the origin of this flux, the origin of this flux is going to be like this. Right? Because divergence of B is 0. Right? So if there's a cube that goes in a circle of the same flux, it goes like that. And it comes out, and it comes straight. Therefore, all the B field that is outside of this circle here, it has to leak out.
Does it leak out in a straight line also, or?
No, it's all over the place then. It's basically, it's semi-infinite, right? So I don't care about it. And somehow it connects at infinity.
Oh, okay.
Right? B field never end. B field always loop. And it's always possible to construct a tube around it. Right? If you follow the flux line, the field line, you can always construct a tube. And it's always conserved. And this is important in say superconductivity, right? You have what's called the type 2 superconductors. When you have a bulk superconductor and you have this flux tube coming out, quantized. Right? It forms a beautiful hexagonal lattice. This is even before the high density superconductivity. It is like the old, like metallic, old alloy superconductor from the 50s, 60s. There are two kinds, type 1 and type 2. In type 2, there's all this flux tube coming out. It's all the same concept. You have to understand all this first. So.